The intellectual landscape of 12th century India provided fertile ground for the synthesis and culmination of centuries of mathematical thought. Within this vibrant milieu, Bhaskara II, or Bhaskara II, composed his monumental treatise, the Siddhanta Siravani, a work whose first part, the Lilavati, stands as a paragon of algebraic and arithmetic exposition. The Lilavati, named with poetic affection for a daughter or perhaps a beloved student, transcends its function as a mere compendium of rules. It presents itself as a complete pedagogical system, a self-contained universe of practical and theoretical mathematics, articulated through a unique blend of metrical verse, evocative prose, and challenging problems. This essay undertakes a rigorous evaluation of the internal claims, methods, and conceptual frameworks presented within the Lilavati, proceeding section by section through its intellectual architecture. The analysis will focus on the substance of Bhaskara's mathematics, assessing the logic of his algorithms, the coherence of his definitions, and the power of his problem-solving heuristics as they are articulated within the text itself. The objective is to build a granular understanding of the work's profound contribution by examining its arguments on their own terms, revealing the depth and sophistication of this enduring mathematical classic. Section 1, the poetic invocation and foundational definitions. The Lilavati commences with a salutation, an invocatory verse paying homage to the deity Ganesha, who is described with imagery related to numbers and immensity. The claim inherent in this opening is the situating of mathematical inquiry within a sacred and cosmological context. This act functions to elevate the discipline of Ganita, or computation, from a purely utilitarian craft to a form of knowledge capable of reflecting divine order. The evaluation of this claim reveals its deep pedagogical purpose. By framing the text in this manner, Bhaskara establishes an authoritative yet accessible tone, inviting the student into a world where numbers are imbued with meaning and wonder. Following this invocation, the text moves to its paribhasha, the section on definitions. Here, the work claims to establish the necessary conceptual toolkit for the mathematics that will follow. It introduces the Dasagunatara Sanjana, the system of decimal place value naming, listing the names for powers of 10 up to Parada, which is 10 to the power of 17. The evaluation of this system shows its complete sufficiency for all subsequent calculations in the book. The definitions are operational rather than axiomatic. For instance, units of measure for weight, currency, and time are provided as direct conversion tables. The internal claim is that mastery of these tables is a prerequisite for engaging with the practical problems. An assessment confirms the practicality of this approach. The framework provides a concrete, worldly basis for the abstract operations to follow, grounding the entire enterprise in the tangible realities of commerce, astronomy, and daily life. The definitional structure itself is a claim for a particular kind of mathematical knowledge, one deeply intertwined with lived experience. Section 2, the 8 fundamental operations and the nature of zero. In the section on Parakarmashtaka, Bhaskara presents the 8 fundamental operations that form the bedrock of arithmetic. These are addition, subtraction, multiplication, division, squaring, cubing and their respective inverse operations, square root and cube root. The implicit claim is that these 8 procedures are exhaustive for all basic computation. An evaluation of the methods reveals a high degree of algorithmic sophistication. For multiplication, or Ganana, Bhaskara describes several methods, including the Tatstha-kriya, which involves breaking down multipliers into their place value components, performing partial multiplications and summing the results in a manner analogous to modern techniques. The efficacy of these algorithms is demonstrable, showing a deep understanding of the distributive property of multiplication over addition. The section on division, or Bhaggahara, contains one of the work's most significant conceptual claims regarding the nature of zero, or shunya. Bhaskara directly addresses the operation of division by zero. He states that a quantity divided by zero results in a kahara, a term meaning that which has 0 as a divisor. He further characterizes this quantity as ananta, or infinite, and clarifies that it is an unchanging entity, a quantity to which nothing can be added and from which nothing can be subtracted. The evaluation of this claim reveals a profound leap in mathematical abstraction. Bhaskara provides a positive definition for the result of this operation, moving the concept of infinity from a philosophical idea to a specific category within the mathematical system. The framework treats this infinite quantity as a logical consequence of the division algorithm, a testament to the internal coherence of his system. The presentation of the rules for operations with 0, including that 0 added to or subtracted from a number leaves a number unchanged, and that a number multiplied by 0 is 0, solidifies its identity as a full numerical entity. Section 3 Fractional Arithmetic and the Ubiquitous Rule of 3. The Lilavati dedicates substantial attention to operations involving fractions, or binah, and to the powerful tool of proportional reasoning known as the Rule of 3, or Trerasika. The section on fractions lays out a comprehensive set of 6 operational types, covering all basic arithmetic with fractional quantities. The claim is that a specific sequence of procedural steps can resolve any problem involving these numbers. For example, his rule for the addition of fractions involves finding a common denominator through the multiplication of the individual denominators, a method that is universally effective. The evaluation of these rules shows them to be algorithmically sound and complete for their intended purpose. The true intellectual core of this portion of the text, however, is the Trerasika. Bhaskara presents this rule as a foundational principle for solving a vast range of practical problems. The structure of the rule is based on 3 given quantities: the PRAM, a macron letter 1E47A or argument, the phalo or fruit, and the ica or requisition. The goal is to find the 4th proportional term. The core claim is that by correctly identifying these 3 quantities in a problem statement, the unknown can be found through a simple formula: the fruit multiplied by the requisition divided by the argument. An evaluation of this claim shows its remarkable power and versatility. Bhaskara extends the principle to the inverse rule of 3, and to more complex rules involving 5, 7, or more quantities, demonstrating a generalized understanding of direct and inverse proportion. The problems posed concerning the wages of laborers or the price of goods confirm that this framework was the central engine of commercial mathematics. The Lilavati's presentation of the rule of 3 asserts that complex relational problems can be distilled into a single, elegant, and universally applicable algorithm. Section 4 The Analysis of Mixed Problems in Commerce and Interest. The chapter titled Misraka Vyavahara, or Mixed Problems, claims to equip the student with the tools to solve complex, multi-step problems involving interest, partnerships, and the combination of different goods. These problems represent a higher level of application, where the fundamental operations must be sequenced correctly to model a given narrative scenario. A key claim within this section is the effective codification of the calculation for interest, or FRIDI. Bhaskara presents a clear formula: the principal multiplied by the time and by the rate, then divided by 100, gives the interest. The evaluation of this formula and its application in the text's problems shows that it pertains exclusively to simple interest. The framework provided is entirely sufficient for this purpose, but it does so without explicitly distinguishing it from compound interest, an interesting omission given the sophistication of other topics. The pedagogical claim of this chapter is that mathematics can be made more engaging through its embodiment in vivid, often poetic, narratives. One famous problem asks for the number of bees in a swarm, where fractions of the swarm are described as visiting different flowers, with a single remaining bee hovering over a lotus. Evaluating this problem reveals its structure as a linear equation with fractional coefficients. The narrative serves as a delightful and memorable container for the abstract mathematical relationship. The challenge for the student is twofold. First, to extract the underlying mathematical structure from the poetic language, and second, to apply the correct sequence of operations to solve for the unknown. This chapter therefore makes a strong case for a pedagogy that weds abstract procedure with imaginative context, asserting that such a union enhances both comprehension and retention. Section 5. The structured world of series and progressions. The section on Sreta Vyavahara addresses the mathematics of series and progressions, both arithmetic and geometric. The central claim of this chapter is that the behavior of such ordered sequences can be fully described and predicted through a set of powerful formulas. For arithmetic progressions, Bhaskara provides the rules to find the sum of the series, the first term, the last term, the number of terms, or the common difference, given sufficient information. For example, he presents the formula for the sum of an arithmetic series, which in modern notation is the number of terms divided by 2, multiplied by the sum of the first and last terms. An evaluation of these formulas confirms their mathematical correctness and utility. Bhaskara presents them as direct tools for computation, often without formal derivation, suggesting a pedagogical focus on application over abstract proof. The problems in this section require the student to manipulate these formulas with considerable algebraic skill. One problem might ask for the first term and common difference of a series given its sum for 2 different numbers of terms, a task that requires solving a system of simultaneous equations. The Lilavati's treatment of geometric progressions is similarly comprehensive, providing rules for finding the sum and other elements of the series. The complexity of the problems, such as those involving sums of squares or cubes of the terms in a progression, demonstrates Bhaskara's assertion that this framework is robust enough to handle higher-order questions about the nature of series. The chapter stands as a testament to the advanced state of algebraic thinking, where generalized relationships are codified into potent computational instruments. Section 6. Geometrical measurement of plane and solid figures. The chapter on Sreta Vyavahara, concerning geometry, makes significant claims about the measurement of area and volume. Bhaskara provides formulas for the areas of triangles, various quadrilaterals, circles, and the volumes of spheres and other solids. One of the most important claims involves the calculation of a circle's area and circumference. He offers 2 values for the ratio of the circumference to the diameter. Our modern pi, for practical or Vyavaharika work, he gives the value of 22 divided by 7. For more precise or sukshma calculations, he provides the highly accurate value of 3,927 divided by 1,250. The inclusion of 2 distinct values is a claim about mathematical practice itself, acknowledging that the required level of precision depends on the context of the problem. This displays a sophisticated metamathematical awareness. In his treatment of quadrilaterals, Bhaskara presents the formula for the area of a cyclic quadrilateral, which is the square root of the product of 4 quantities, where each quantity is the semiperimeter minus one of the sides. This is an exact formulation corresponding to Brahmagupta's theorem. His presentation of this rule, as a given fact, without a derivation, is consistent with the text's overall pedagogical approach of providing powerful tools for immediate use. For the triangle, he correctly provides both the standard formula of 1/2 the base times the height and Heron's formula for the area given 3 sides. His treatment of the right-angled triangle includes a clear articulation of the relationship between the sides, what is now known as the Pythagorean theorem, and its application in various geometric constructions and problems. The chapter asserts a comprehensive mastery over the metrical aspects of 2- and 3-dimensional space. Section 7. The mnemonics and the mathematics of excavations. Following the more abstract geometry, the Lilavati moves into highly practical applications in chapters on mnemonics, Vyavahara, and on calculating volumes of excavations and stacks, Vyavahara. The section on the gnomon, the vertical rod used to cast a shadow, claims that the principles of geometry, specifically those of similar triangles, can be used to solve problems of distance and height. A typical problem involves determining the height of a lamp post by knowing the length of a gnomon and the lengths of the shadows cast by both the gnomon and the post. An evaluation of the method shows it to be a direct and flawless application of the properties of similar triangles, linking abstract geometric ratios to tangible astronomical and surveying problems. This section effectively claims that mathematics is the essential bridge between terrestrial measurement and celestial phenomena. The chapter on excavations presents methods for calculating the volume of earth removed to create wells, tanks, or other structures. It provides formulas for regular solids as well as for frustums of pyramids and cones, which are common shapes for such excavations. The claim here is the mathematization of civil engineering. The formulas provided, for example for the volume of a frustum, are accurate and demonstrate a sophisticated grasp of solid geometry. By including these topics, Bhaskara asserts the role of the mathematician in practical, large-scale projects, positioning Ganita as a core discipline for the architect and the engineer. The problems are specific and grounded, asking for the volume of a trench with sloping sides, requiring the student to apply the correct geometric model to a real-world scenario, thereby reinforcing the utility and power of the mathematical framework. Section 8, the pulverizer's indeterminate power. Perhaps the most advanced topic in the Lilavati is the Kataka, a powerful algorithmic method for solving indeterminate linear equations. These equations take the general form where a dividend, when divided by a first divisor, leaves a certain remainder, and when divided by a second divisor, leaves another remainder. The goal is to find the dividend. In modern terms, this is equivalent to solving systems of linear congruences. The Kataka, or pulverizer, is an algorithm that finds integer solutions to linear Diophantine equations of the former times x plus or minus c equals b times y. The primary claim of this chapter is that this intricate, iterative algorithm can solve a class of problems that appear unsolvable with more elementary methods. The process Bhaskara describes is remarkably elegant. It involves a sequence of reciprocal divisions of the coefficients, forming a column of quotients, and then working backwards up the column with a process of multiplication and addition to generate solutions. An evaluation of the Kataka reveals it to be identical in its logical structure to the extended Euclidean algorithm. The power of this method is immense, particularly in its application to astronomical problems, which often involve finding planetary positions after a certain number of cycles, a problem that naturally produces indeterminate equations. By including the Kataka in the Lilavati, which is ostensibly an introductory text on arithmetic and algebra, Bhaskara makes a profound claim about the scope of Patagonita or elementary mathematics. He asserts that this field extends to the solution of indeterminate problems, blurring the line between arithmetic and higher number theory. The presentation is purely algorithmic, a sequence of precise instructions that, when followed, pulverizes the problem into a Section 9, the generative logic of combinatorics. The final mathematical chapter of the Lilavati, Ankapasha, is dedicated to permutations and combinations. The core claim of this section is that the number of possible arrangements of a set of distinct items can be calculated systematically. Bhaskara presents the rule for generating permutations, which he calls prastara. His method is clear. The number of permutations of a set of n distinct digits is the product of the integers from 1 up to n, which we recognize as n factorial. He provides illustrative examples, such as finding the number of variations of a verse from a medical text by rearranging the syllables, or calculating the different ways the 10 attributes of the god Shiva could be held in his 10 hands. An evaluation of his method confirms its correctness and pedagogical clarity. He then proceeds to combinations, or vikalpa, providing the formula for finding the number of ways to choose k items from a set of n items. His formulation is equivalent to the modern binomial coefficient formula. The problems posed, such as finding the number of possible combinations of pleasant and bitter tastes from a set of 6 fundamental tastes, demonstrate the application of this theory to philosophical and practical classification systems. By including this chapter, the Lilavati claims that mathematics provides a language for understanding structure and variety itself. It moves from calculating fixed quantities to calculating the potential for variation, a significant step in abstraction. The chapter showcases a developed understanding of combinatorial principles, asserting that even the vastness of possibility can be quantified and understood through logical rules. A fittingly powerful conclusion to the book's mathematical exposition. Conclusion: a systematic evaluation of the Lilavati's internal claims reveals a work of extraordinary intellectual coherence and pedagogical vision. Bhaskara II constructed a text that functions simultaneously as a comprehensive primer in arithmetic, a sophisticated treatise on algebra, and a poetic celebration of the mathematical arts. From its opening invocation to its final exploration of combinatorics, the work consistently delivers on its promise to provide a complete system. For Patagonita, the evaluation of its algorithms from the basic operations to the powerful Kataka confirms their efficiency and logical soundness within the mathematical framework of the era. The text's claimed practical utility is substantiated through a vast array of problems drawn from commerce, geometry, astronomy, and civil engineering, all designed to demonstrate the direct applicability of the concepts being taught. The Lilavati's most profound assertion, however, lies in its very form, the fusion of rigorous, abstract procedure with memorable, narrative problems. Bhaskara's work argues that mathematics is a living discipline, a tool for both understanding the cosmos and engaging with the practicalities of the human world. The clarity of its methods, the sophistication of its solutions to indeterminate problems, and its unique articulation of mathematics as a discipline of both beauty and power, solidify the Lilavati's standing as a masterpiece of intellectual history, a work whose claims are as robust and compelling today as they were in the 12th century.